Alright, hello everybody. This video is going over the third lesson in Unit 3, which is on solids, liquids, and gases. So matter exists in three main states, solid, liquid, and gas. The difference between these states come from how far apart the particles are and how much they move. In solids, particles are going to be tightly packed and they're going to vibrate in place. In liquids, they're going to be close, but they can move past one another. And in gases, they are far apart and can move freely. For AP Chemistry, you should be able to represent these differences using particle level models, but you do not need to interpret phase diagrams for the actual exam. Solids can be crystalline or amorphous. On the right side of the screen here, we have two covalent network solids. One is crystalline SiO2, which is considered quartz. And then we have its allotrope amorphous SiO2, which is glass. Clearly, these are two different types of structures. On the left, the quartz, we have a three-dimensional structure that is going to be very strong and withstand a lot of energy in order to break it. Whereas our amorphous SiO2 does not have that strength in a 3D structure. It does not have an orderly arrangement, and it has no long-range ordered structure. So that is easier to break if we're looking at these two specific solids. I hope you know that quartz is going to have a much higher melting point than glass would, and that's simply because of its structure. In both substances, because they are solids, they're going to have a limited range of motion. The actual particles are not going to move, but they are going to vibrate. Liquids have particles that stay close together, but they can move and collide constantly. Their behavior is going to depend on the strength and type of intermolecular forces, like dipole-dipole interactions or hydrogen bonding. Another factor that can influence their behavior is temperature. When we increase the temperature of a liquid, those particles are going to have more energy and move faster, so their average kinetic energy will be greater, which means they're going to behave a little differently than something that would have a lower temperature. And compared to solids, particles in liquids have more freedom to move, but they are still held together by attractive forces, unlike gases where particles can move independently of one another. In most substances, solids and liquids have similar molar volume because their particles remain close together in both phases. However, water is a very important exception to that. Because water has strong hydrogen bonds, they're going to force water molecules into a hexagonal structure when they're frozen, which you see on the bottom right there. And because of that, it's going to leave extra space in between molecules. And that's why ice is less dense than liquid water and it floats. And that's also why if you put water in a plastic bottle and put it in the freezer, it's most likely going to expand because of that hexagonal shape and the space in between the molecules. Gases consist of particles in constant motion. They're going to move freely and collide with each other constantly. The spacing between particles and how often they collide depends on the temperature, pressure, and volume. Because intermolecular forces are very weak in gases, they do not have a fixed shape or volume, and they expand to fill any container. At higher temperatures, particles move faster and spread farther apart, which supports Charles's law. Solids, liquids, and gases differ in both their properties and particle behavior. Solids have a definite shape and are very difficult to compress, and their particles only vibrate in fixed positions. Liquids have no shape, they flow to fill a container, and they are harder to compress with particles that move freely while staying close together. And gases have no fixed shape or volume, they are easily compressed, and their particles move independently with much higher energy, colliding with each other and the walls of its container. Now let's move on to the next lesson of Unit 3, which is on the ideal gas law. So the ideal gas law, which is PV equals nRT, connects the main properties of gases: pressure, volume, temperature, and moles. It explains gas behavior both macroscopically through measurable variables and microscopically through the motion of particles. For AP chemistry specifically, you need to be able to explain how changing one variable will affect the others and use the equation to predict relationships in real or mixed gas samples. Gas pressure comes from particles colliding with the walls of their container. The more frequent the collisions, the higher the pressure. Increasing temperature makes particles move faster or increases their average kinetic energy, which is going to raise the pressure if the volume stays constant. Decreasing volume is going to force particles into a smaller space, which is going to raise the pressure because if they're in a smaller space with the same number of molecules, they're going to collide with each other and the walls of the container more frequently. And adding more gas particles is going to increase collisions, which raises pressure or volume depending on the container. And all of these ideas are going to connect directly to Charles' law, Boyle's law, Avogadro's law. Temperature in gases is really a measure of the average kinetic energy of the particles. As temperature increases, particles are going to move faster, and that's all that means. On the AP exam, remember that temperature links directly to particle motion. And standard temperature and pressure, or STP, is something that you will hear a lot, and it is defined as either 0 degrees Celsius or 273 Kelvin for temperature, or 1 atmosphere, 760 millimeters of mercury, 760 torr, or 101.3 kPa for pressure. And today we're just going to do some examples with Boyle's, Charles, Gay-Lussac's, and the combined gas law. And here is a table that kind of summarizes all 4 of those. Boyle's law shows that pressure and volume are inversely related. So if volume increases, pressure will decrease. And if volume decreases, pressure will increase. And that's because the number of particle collisions with the container is going to change. So the formula for Boyle's law is P1V1 equals P2V2. So let's do an example with that. What is the final pressure of a gas that initially has a pressure of 10 atm at 50 liters if the volume is reduced to 25 liters? So we are looking for the final pressure, which means we are looking for P2. So if we are looking for P2, our new equation would be P2 equals P1V1 over V2. So we know our initial pressure is 10 atm. Our initial volume is 50 liters. Our final volume is 25 liters. Now we see our liter unit will cancel out, so we're left with atm. Since it did not ask for a specific pressure unit, we can just assume that it's going to let us keep it in atmospheres. So now we do 10 times 50, which is 500, divided by 25. And that gives us 20 atmospheres. Now looking at what we were given, we took our initial volume and decreased it, and our initial pressure went from 10 to 20, so it increased. So we decreased volume, which increased pressure. Charles' law shows that volume and temperature are directly related as long as pressure and the amount of gas stay constant. When temperature increases, particles move faster and collide more, so the volume expands to maintain that same pressure. The formula for Charles' law is V1 over T1 equals V2 over T2, with temperature measured in Kelvin. For example, a balloon with 750 milliliters of gas at a temperature of 235 degrees Celsius is cooled with the same pressure to a temperature of 50 degrees Celsius. What is the final volume of the gas in the balloon? So we are looking for final volume, which is V2. So our new equation will be V2 equals V1 T2 over T1. So our first initial volume is 750 milliliters. Our second temperature is 50, and whenever we're doing the ideal gas law, we have to convert to Kelvin. So 273 plus 50 is going to give us 323 degrees Kelvin. And then our initial temperature goes on the bottom, which is 235 plus 273. Which is going to give us 508. Now you can see our temperature units cancel out and we're left with milliliters. Since it did not ask for a specific unit of volume, we're just going to keep it at milliliters. So we have 750 times 323 divided by 508, and that's going to give us 477 milliliters. So as you can see, our temperature went down from 235 to 50, and our volume also went down from 750 to 477. Gay-Lussac's law shows that pressure and temperature are directly related when volume and amount of gas stay constant. At temperature increase, particles are going to move faster, which causes more frequent and stronger collisions, leading to higher pressure. The formula is P1 over T1 equals P2 over T2 with the temperature in Kelvin. For example, if the pressure of a sample of 1 mole of an ideal gas is increased from 2 atmospheres to 3 atmospheres at a constant volume, and the initial temperature was 20 degrees Celsius, what is the final temperature of the sample? Now again, it's not telling us the actual unit to answer in. We can assume if it's AP chemistry, it will accept Kelvin. However, if it gave us Celsius, we're going to also answer in Celsius. But just remember, whenever you are using temperature in an ideal gas equation, you have to convert it into Kelvin first. So if we're looking for final temperature, that means we're looking for T2. So T2 is going to equal T1 times P2 over T1. So our initial temperature is going to be 20 degrees Celsius plus 273 will be 293 Kelvin. Our final pressure will be 3 atm. And our initial pressure is 2 atm. So our pressure units are canceled out and we're left with Kelvin. So we have 293 times 3 divided by 2 gives us 439.5 Kelvin. Now again, since we started in degrees Celsius and it did not specify, usually it wants us to answer in degrees Celsius. So in order to take that out of Kelvin, we want to subtract 273. So our final answer would be 166.5 degrees Celsius. Avogadro's law states that volume and the number of moles of gas are directly related as long as temperature and pressure stay constant. Adding more gas particles is going to increase collisions, so the container must expand to maintain that constant pressure. And the formula is going to be V1 over N1 equals V2 over N2, showing that volume is proportional to the amount of gas. The combined gas law relates pressure, volume, and temperature when the amount of gas stays constant. It combines Boyle's, Charles, and Gay-Lussac's law into one formula, which is P1V1 over T1 equals P2V2 over T2. This law is useful when more than one variable changes at the same time. For example, if the volume of the gas is halved and the temperature decreases, the pressure will adjust depending on both changes together. So let's look at this example. A sample of ideal gas is heated in a 2-liter vessel at a temperature of 320 Kelvin. The pressure in the vessel is 2.5 atmospheres. What is the new pressure in the vessel if the volume is halved and the temperature is reduced to 250 Kelvin? So we are looking for new pressure, which means we're looking for P2. So our new equation will be P2 equals P1 V1 T2 over T1 V2. So our initial pressure is going to be 2.5 atmospheres. Our initial volume is a 2-liter vessel. Our final temperature is going to be 250 Kelvin. Our initial temperature is 320 Kelvin. And our final volume is halved, so it'd be 1 liter. So now you can see our Kelvin units cancel out and our liter units cancel out, so we're left with atmospheres. And now we just solve. So we have 2.5 times 2 times 250 divided by 320. That's going to give us 3.91 atmospheres. Now, all those laws we just talked about, Gay-Lussac, Charles, Boyle's combined, those are all derived from the ideal gas law. The ideal gas law is written as PV equals nRT, where pressure, volume, moles, and temperature are related through the gas constant R. It's based on the assumption of kinetic molecular theory, which states that gas particles have negligible volume, no intermolecular attractions, and perfect elastic collisions. In reality, gases do have small volumes and weak attractions, but under most conditions, the ideal gas law does give us accurate results, even if they're not ideal gases. And when we're working with gases, you will hear the word STP a lot. Remember, at STP, which is standard temperature and pressure, at 273 Kelvin and 1 atm, 1 mole of an ideal gas occupies 22.4 liters, which is found in your reference sheet. You do not have to memorize that. In gases, we assume collisions are elastic. That means when gas particles collide with each other or the walls of the container, no kinetic energy is lost. And that means energy and momentum are going to be fully conserved. In reality, most collisions in nature are inelastic, where some kinetic energy is converted into other forms like heat. But for the ideal gas law and kinetic molecular theory, we treat collisions as perfectly elastic, so calculations stay accurate. The ideal gas law applies to mixtures of gases as well as pure gases. According to Dalton's law, the total pressure of a gas mixture equals the sum of the partial pressures of each individual gas. Because each gas behaves independently, we can just add the 2 pressures up and it will give us the overall pressure. All right, let's wrap up this lesson with an example problem. Deep sea divers must use special gas mixtures in their tanks rather than compressed air to avoid serious problems like the vents. At depths of about 350 feet, divers are subject to a pressure of approximately 10 atmospheres. A typical gas cylinder used for such depths contains 51.2 grams of O2 and 326.4 grams of helium and has a volume of 10 liters. What is the partial pressure of each gas at 20 degrees Celsius, and what is the total pressure in the cylinder at this time? So you can see we're given a pressure unit, we're given volume, and we're also given temperature. So all we really need is moles in order to find pressure. So here we have 51.2 grams of O2, and if I want to use that in the ideal gas law, I have to get it into moles. So in 1 mole of O2, I have 32 grams of O2. That's going to give me 1.6 moles of O2. And I'm going to do the same thing for helium. So 326.4 grams of helium. And we know in 1 mole of helium, that is equal to the molar mass of helium. So it's going to give us 81.6 moles. Now we can solve for the pressure of O2 and the pressure of helium and then add them together to get the total pressure. So in order to get pressure, we want to be solving for P. So we just solved for N, which is 1.6. Our R value for atmospheres is 0.08206. And then our temperature would be 20 degrees Celsius plus 273, which would be 293. And then we're going to divide those 3 by the volume, which is 10 liters. So 1.6 times 0.08206 times 293 divided by 10 is going to give us 3.85 atmospheres of pressure for O2. Now we're going to do the same thing for helium. So we want the pressure. We already have the moles at 81.6. We have our R value because we know we're using atmospheres, so 0.08206, and that is on your formula sheet. You do not have to memorize that. And then our temperature is the same, 293, and our volume is the same at 10 liters. So we have 81.6 times 0.08206 times 293 divided by 10 is going to give us 196 atmospheres of pressure for helium. So those are our partial pressures of each gas, and now we need the total pressure, and to get the total pressure we're just going to add those up. So our total pressure is going to be 200 ATM. All right, I hope that helped. If you have any questions, please feel free to reach out. I'm happy to help. Have a great day. Bye.